This is our first FRQ from assignment 10, which is QQTs from unit 4. So what we have here is a dart with a mass md launched towards a block of mass mb suspended from a string of length L as shown. The dart is moving horizontally with a speed v immediately before it strikes the block and remains embedded. So hopefully you're thinking perfectly inelastic collision. The dart block system then swings up to a point at which its center of mass reaches a maximum height h above its starting position, as shown on the right. The block's mass mb is greater than the dart's mass md. Great, so part A says indicate which object, the dart or the block, if either, experiences an impulse of larger magnitude during the collision. So remember that impulse is equal to F times delta t, which is equal to m times delta v. So there's two ways you could argue this. The answer is they experience the same impulse. My argument was they both experience equal force because they're an action-reaction pair. They experience that force for the same time, therefore their impulse is the same. You could also argue that the change in momentum for each object is equal due to conservation of momentum, and that since impulse is equal to a change in momentum, they're equal that way as well. So 1 point for that, and the rubric was correct explanation using either force and time or change in momentum. That's part A. Part B says if the speed of the dart, as it embeds itself into the block is greater than v, how would the maximum height reached by the center of mass compare to h? Explain your response without deriving or manipulating equations. So a higher speed is going to equal a higher h, or a larger h. You need to address both conservation and conservation of energy in this explanation. Here's what I wrote. If the speed were increased, the height would increase. Okay, the dart transfers its momentum to the dart block system. That system then converts its kinetic energy into gravitational potential energy. The kinetic energy will be greater if the speed was greater, and more kinetic energy leads to a larger gravitational potential energy, which leads to a higher height of the block. So 2 points there. One for saying that the final height is greater, and then another point for using conservation of momentum to indicate that the speed will be higher, and then conservation of energy to indicate that the height would be higher. So that's part B. On to student 1 and student 2. Student 1 says the speed of the system at height h is 0. Since it's moving in a circular motion and centripetal acceleration is given by v squared over r, then its acceleration must be 0. Student 2, well, let's deal with student 1 first. The speed of the system at height h is 0, so the first statement is correct. But the second statement is incorrect. The acceleration is not 0. Obviously, maybe not obviously. Just because something stopped moving doesn't mean its acceleration is 0. Think of tossing anything up in the air, which is essentially what we're doing here, or something on a spring. It could stop. In fact, sometimes when there's when it's not moving, it's experiencing the maximum amount of force sometimes. So don't get sucked into that. The second equation is wrong. How about student 2? The acceleration of the height at h can't be 0, or the system would not swing back down. The acceleration must be equal to g at height h. So statement 1 is correct. The acceleration at that height can't be 0 because it would not swing back down. If it weren't, it would just stay right there. But the acceleration is not equal to g. Remember, we've done something similar to this before. At the top there, we do have a component of g, but we also have a component of tension. So the acceleration is going to be along those lines. So the first statement was right. The second statement was wrong. Okay, now moving on to g. The students correctly derive an equation that is h equals 1 over 2g. Up here we have, in this almost impossible to read, mass of the dart times the velocity over the mass of the dart plus the mass of the block squared. Right? Explain how this supports your claim in part B. So it doesn't ask if it's right. They say it's already right. So what we said in part B is if we have a larger velocity, we'll have a higher height. And since height and velocity are directly proportional, or at least one goes up, the other goes up in this equation, that's why. Okay, so the reason this equation supports our claim is that if v increases, h increases, right? Because of the way they are in the formula. So the rubric there says 1 point for using a functional dependence. So hopefully at least everybody gets that point on whatever QQT you get. Try to relate the information given through that formula and ask yourself, if blank increases, what happens to the other thing? And see if that supports your claim that you make earlier in the process. Then another point for saying that as velocity increases, h must increase as well. So hopefully these are getting a little bit better for you guys, or a little bit easier. And then we can't forget the graph, right? What could we graph to get a straight line whose slope could be used to find the acceleration? Okay, we don't need to tell what to graph so that the slope is the acceleration. Nope, we don't need that. Just what can we do that's going to get linear? So we've got h by itself on one side and v, but v is squared. So we want to either graph h versus v squared, or we could graph rad h versus v. You could do similar things that are less obvious, but those are probably the two options there. So we get 1 point for putting h on one axis, 1 point for putting v on the other axis, and then 1 point for what they call, let me say this the right way, a correct power relationship. Right, so you couldn't do h versus v. That's not going to go. You can't do h squared versus v. It's got to be either h versus v squared or rad h versus v. So that's for h. Finally, now we have let these the block dart system swing, and we are graphing the vertical position versus time. Then we have a second group of students that makes a sum change to this experiment, and they get the graph from group 2. So the question is, what happened? All right, indicate the single difference either in the dart mass, initial dart speed, block mass, or string length that leads to the difference. So what you should notice looking at the graphs is that t decreased, right? The period decreased. The time it took to go from maximum back to maximum decreased, right? Now, the period of a pendulum, and this is on your formula sheet, so don't forget, 2 pi L over G. So the only way we can change the period of this oscillation is by changing the length of the string or going to another planet, all right? That wasn't one of the options, so string length is it, okay? Now let's be clear. In order for the period to decrease, the length of the string should also decrease. Okay, so we get 1 point for recognizing that the period got shorter, 1 point for saying that the only thing that determines the period of a pendulum is the length of that string, and 1 point for saying the length must be shorter. So that's the first FRQ from assignment 10.